So in the previous video, we found out that the potential energy is given by U. So U is equal to G M M over R, and there's a minus at the front. So G is a universal gravitational constant. M is uh, the mass of the planet, and small m is the mass of a satellite in our case, and r is the distance of the satellite from the center of the planet. So we have kinetic energy. Let's use K for kinetic energy here. So K. So kinetic energy is given by half mv squared. So m is the mass of the satellite and v is the linear velocity. But previously we discussed that the force, the gravitational force, which provides a centripetal force for the satellite to complete its orbital motion. So we have an equation that the centripetal force is equal to the gravitational force. So centripetal force is given by mass time acceleration. So m acceleration is given by v square over a for an object that's going through a circular motion. So in this case, let's put r here instead of a because that's sometimes get confused with that. So instead of that, we put r is equal to the gravitational force is given by g m m m m over r squared. So what we want to find out is half mv squared, right? So if mv squared over r is this, half mv squared is equal to, what we're doing is we are multiplying by half and then r. So we do the same there. So we will get g m m over 2r because r will cancel, and then we have got we are dividing by the 2. So that's the equation for the kinetic energy here. So we got the potential energy, which is Gmm over R, and the kinetic energy is Gmm over 2R. So what's the total energy then? The total energy is equal to U plus K. So in our case, it's going to be minus Gmm over R plus Gmm over 2R. So we will get minus Gmm over 2R. So looking at this, we have kinetic energy Gmm over 2R, and the total energy is minus Gmm over 2R. So let's just look at these values, because the potential energy is negative, and we got the value Gmm over R, and the kinetic energy is positive. So what happens to a satellite in orbit? When it starts to orbit, it energy is increased, total energy is increased. So potential energy is a negative value. That means the negative value will be reduced. For example, if it's minus 20, the potential energy, and after adding the kinetic energy, it will become minus 10 because we are adding energy to it. So we go, that's the potential energy. This is the kinetic energy, which is a positive one. And we get a minus value for the total energy. So minus Gmm over 2R and minus Gmm over R. If you just look at the quantity without the sign, whether it's minus or plus, here we are dividing by R, here we are dividing by 2R. So this is a smaller number, that's a bigger number. But because we have a minus at the front, this is greater than that. So adding a kinetic energy to the potential energy, the energy is increased. There's another interesting relationship we can find here is that the total energy, which is minus gmm over 2r, is equal to minus k, because k is gmm over 2r is minus. So we can write on E total is equal to minus k, because the total energy is minus gmm over 2r, k is equal to gmm over 2r. So E total is minus k. We can also say the E total is equal to U by 2. Quite interesting, because what's happening is that we have the potential energy for a satellite that's orbiting the Earth, and the total energy is half of the potential energy. So, but remember, it's half of the potential energy, but that is in terms of the magnitude. So before it was minus gmm over r, and now it's minus gmm over 2r, so it is halved, but it's increased because it's minus. So less minus value is actually a bigger one. So in summary, the total energy of the satellite is increased. 20 kilogram mass is launched vertically from the moon's surface at a velocity 1200 meters per second. And we got the radius 174 kilometer, and we got the mass of moon. So what we want to find out is two things. One is that they're asking us to find the energy difference, the potential energy difference between the moon's surface and the value at the distance 500 kilometer from the moon's surface. And the second one is they're asking us to find the velocity at this place. But there's something else that's given in this question is that to ignore the moon's rotational and orbital motion. So what are the concepts that we should be aware of here? If we use the conservation of energy, that law of conservation of energy, the energy here and the energy here is the same. What's happening is that we provide a kinetic energy, and that is converted into potential energy, and some kinetic energy will be left. That's why it has some velocity. They're asking us to find the velocity as well. So the difference in potential energy between this one and this one is equal to the kinetic energy that was given to the object to lift the object from here to here. So what we have done here is that we have the equation for UA and UB. UA is equal to minus gmm over r, and UB, which is here, is gmm over r plus h. R is the radius of the moon, h is the altitude, which is given as 500 kilometer, which is 500 times 10 to the power 3 meter. So what we're doing is the difference of between this and this potential energy is equal to UB minus UA. This is the final one, it's the initial one, UB minus UA, and we substitute what we have got here. So minus gmm over r plus h, and minus minus, that will become plus. And what we are doing is we are substituting the values here, and g is 6.67 minus times 10 to the power minus 11. And then for the mass, it's 7.35 times 10 to the power 22 and time 20 here. And we got UA here, where the difference is that we don't have r plus h instead of r, the radius. So the energy difference, if you put that in the calculator, you'll get 1.26 times 10 to the power 7 joules. So that's the answer for A. For the second question here, calculate the velocity of the 200 kilogram mass at an altitude of 500 kilometers. So they're asking us to find the velocity of this object. So what's happening here? We discussed this before. When we are, the object has got 1,200 meters per second. When it goes up by 500 kilometers, now the velocity is reduced. So what's happening is that the kinetic energy is used for the object to gain the potential energy. So we can say that the delta K is equal to delta U. So delta K is equal to delta U. So the change in the potential energy that we found out, that is 1.26 times 10 to the power 7 joules. So what's the change in kinetic energy then? We know the kinetic energy at this place because we know the velocity. And here, say for instance, if the velocity is v, so that is half mv squared. That's the final kinetic energy. And the kinetic energy here is, we know that is half m times v squared, which is 1200 times squared. So the difference in the kinetic energy is same as the difference in the potential energy. But we gained the potential energy, but we lost the kinetic energy. So this minus this equal to this minus this. So this minus this, which is the loss in the kinetic energy, is same as the potential energy here minus the potential energy here. So by using this principle that I got this value here, so the difference in the kinetic energy is kf minus ki. Kf is equal to half mv squared. That's what we want to find out the velocity. Ki is equal to half times 10 times v squared with this one. So kf minus ki is equal to delta u, which is the potential energy that we gained is same as the kinetic energy we lost. And using those values, we will find the velocity is 424 meter per second.